When you watch a Starship launch and see the vehicle arc over, tilting from vertical to nearly horizontal during ascent, that's not the rocket turning toward its destination. That maneuver, called a gravity turn, is the rocket finally doing its actual job. The vertical climb at the start just clears the thickest part of the atmosphere. The sideways acceleration is everything. Let that 97% figure sit for a moment, because once you internalize it, Starship's design choices stop looking arbitrary and start looking inevitable. 33 Raptor engines on the Super Heavy booster, 6 more on the upper stage, a combined height of 121 meters, taller than the Statue of Liberty. Practically every headline about Starship leads with the size. World's biggest rocket, world's most powerful rocket. But here's a misconception worth demolishing. Starship isn't revolutionary because it's big. Saturn V was big. The Soviet N-1 was big. Being big is, in a certain sense, the straightforward part of rocket design. You scale up the tanks, you cluster more engines. What makes Starship potentially the most important vehicle in the history of spaceflight is something entirely different. Both stages come back. To see why that's transformative, consider an analogy. A Boeing 747 costs about $350 million. The jet fuel for a transatlantic flight costs roughly $150,000. The ratio is staggering. The vehicle costs over 2,000 times more than the fuel that moves it. Nobody would dream of building a disposable 747 for each crossing. And yet, for 70 straight years, that's exactly what the space industry did with rockets. The Saturn V that carried Apollo 11 to the moon cost approximately $1.2 billion in today's money. It flew once. Its first stage sank into the Atlantic. Its second and third stages were either discarded in orbit or crashed into the lunar surface. $1.2 billion of precision engineering used once and abandoned. The physics explains why this insanity persisted. Our full video on this was posted recently. Check it out on our channel profile now.